Hello student, today we will discuss about PYQS of capacitance. First question that was asked in NEET 2016, a parallel plate capacitor of area A and plate separation is D and a capacitance C is filled with a 4 dielectric material having dielectric constants K1, K2, K3 and K4 as shown in figure. That is your given figure. That 4 dielectrics are arranged in this order. If a single dielectric material is to be used to have a same capacitance C in a capacitor, then the dielectric constant K is given by. We have to find out the equivalent capacitance of this arrangement. First of all, these above 3 capacitors are connected as per this figure, that above 3 capacitors C1, C2 and C3, that above 3 capacitors are connected in parallel combination, and then it is connected in series with C4 capacitor. So C1, C2, C3, first of all these above 3 capacitors are connected in parallel, and then this combination is connected in series with C4. So based on this, the basic formula for parallel plate capacitor having capacitance C is equal to epsilon A by D, epsilon naught A by D. But here there is a dielectric is inserted in between this parallel plate of capacitor. That's why the capacitance is increasing by K times. So the new capacitance C becomes K times epsilon naught A by D. Now, based on this, that C1 is equal to K epsilon naught A by 3, denominator D by 2, because here that first dielectric material having the area equal to A by 3 and the distance or the width is D by 2. Similarly, for K2 is also A by 3, area is A by 3 and the distance or width is equal to D by 2. Similarly, for K3 is also same. So based on this, C is equal to epsilon naught A by D. From this formula, the parallel plate capacitance C1 is equal to K1 times epsilon naught A by 3 in denominator D by 2. So C1 is equal to 2 by 3. After simplify, the C1 comes out to be 2 by 3 K1 epsilon naught A by D multiply by K and divide by K, dielectric constant. So that C1 is equal to 2 by 3 K1 K times epsilon naught A by D in bracket, in denominator it is equal to multiply by 1 by K. So C1 comes out to be, the value of C1 is equal to 2 by 3 K1 upon K into C. So based on this, similarly we can write for C2, that is 2K2C by 3K, and in place of C3 we can write 2K3 by 3K into C. For C4 capacitance, it is equal to K4 times epsilon naught A D by 2, because area for the fourth capacitor it is A. See here, that is area is equal to A for the fourth dielectric, and the distance or width is equal to D. Width is equal to D by 2. So here the width of the fourth dielectric, that is equal to half, that is D by 2, and area remains same. So K4 times epsilon naught A divided by D by 2. So it becomes K4 2 epsilon naught A by D multiply by K divided by K. It comes out to be C4 is equal to 2 K4 by K into C. Now that equivalent capacitance of parallel combination CP is equal to, that is CP is denoted as the equivalent capacitance of parallel combination, that is the simply addition of C1, C2 and C3 capacitance. So CP is equal to 2C by 3K is taking outside of bracket, because it is common term in C1, C2 and C3, that is 2C by 3K. In bracket, the remaining quantity is K1 plus K2 plus K3. So 1 upon Cp is nothing but 3K by 2C, the reciprocal of Cp, that is 1 upon Cp is equal to 3K by 2C, in bracket 1 upon K1 plus K2 plus K3. Now the equivalent capacitance of the whole combination, that is 1 upon C equivalent is equal to 1 upon Cp plus 1 upon C4, because these three capacitor which is connected in parallel, these are connected in series with this C4. So C1, C2, C3, that the equivalent capacitance is Cp, and Cp and C4 are now connected in series combination. So for series combination, 1 upon C equivalent is equal to 1 upon Cp plus 1 upon C4. So taking 1 upon C equivalent as 1 upon C, and in place of 1 upon Cp, that is we can write from this equation, that is 3K by 2C in bracket 1 upon K1 plus K2 plus K3, and in place of 1 upon C4 we can write here K upon 2K4 into C. So after putting the value of Cp and C4, taking common K by 2 term is common, from these two terms that and C get cancel out in on either side of the equation. So the remaining term on LHS side is equal to 1 is equal to K by 2 in bracket. The remaining quantity is 3 plus K, 3 divided by K1 plus K2 plus K3 plus K4. So 2 by K, after rearranging the equation, 2 by K is equal to 3 upon K1 plus K2 plus K3 plus K4. That is the required answer. Question number 1, option C is correct. Question number 2, a series combination of N1 capacitor, each of value C1, is charged by the source of potential difference 4 volt. When a series combination of N1 capacitor are connected in series, each of having the value of C1 is charged by the source of potential difference of 4 volt. When another parallel combination of N2 capacitor, each having the value of C2, is charged by the source of potential difference V, it has a total or same energy stored in it as the first combination has the value of C2 in the terms of C1. We have to find out the value of capacitance C2 in terms of C1. That was asked in AIPMT 2010. So first of all, in case of the series combination, the equivalent capacitance CS is equal to C1 by N1. For series combination, the formula is CS, that is equivalent capacitance CS is equal to C1 upon N1, because each capacitance is identical, having identical value, that is of C1, and divided by N1 capacitor, because there are N1 capacitor are connected in series combination. So CS is equal to C1 upon N1, and voltage in series is given as Vs is equal to 4 volt. So energy stored in it, ES is equal to 1 half CV square, so 1 half CS into Vs square, where CS is nothing but C1 upon N1 and Vs is equal to 4 volt. So ES is equal to 1 half C1 by N1 in place of CS, and Vs square in place of Vs square we put here value 4 volt whole square. That means the energy stored in case of series combination ES is equal to 8 times C1 V square upon N1. That is equation number 1. Now in case of parallel combination, the equivalent capacitance Cp is equal to N2 times C2. So in case of parallel combination, the equivalent capacitance is denoted as Cp. Cp is equal to N2 times C2 because there are N2 capacitors connected in parallel combination, and Vp is equal to V. That your equivalent voltage in case of parallel combination is equal to V volt. So energy stored in parallel combination EP is equal to 1 half Cp into Vp square. So in place of Cp we write N2 into C2, and in place of Vp is equal to V, that is Vp square is equal to V square. So EP is equal to 1 half N2 times C2 into V square. That is equation number 2. Now in data that is given that both energy, that parallel combination and energy stored in series combination as well as energy stored in parallel combination both have similar value. So what is the value of C2 in terms of C1? So equating these two equations, ES is equal to EP, that energy stored in series is equal to energy stored in parallel combination, that is 8 times C1 V square upon N1 from equation number 1, and N2 times C2 V square upon 2. So after simplify this, the value of C2 comes out to be 16 times C1 upon N1 into N2. That D is the correct option for question number 2. Question number 3, a parallel plate air capacitor has a capacity C. The distance of separation between the plate is D. Potential difference is V. Is applied between the two plate of capacitor. The force of attraction between the plate of parallel plate air capacitor is. So here the required answer is CV square by 2D. That is the force of attraction between the parallel plate capacitor, parallel plate air capacitor. That was asked in AIPMT 2015. So first of all, the force of attraction between the plate is F is equal to Q square upon 2A epsilon naught. That is the force of attraction between the two plate of air capacitor. That is F is equal to Q square upon 2 times A epsilon naught. In place of Q, we can write Q is equal to CV because Q is proportional to V and Q is equal to CV, that is your proportionality constant, that is also called as capacitance. And for parallel plate capacitor, the capacitance C is given as epsilon naught A by D. So in place of epsilon naught into A, we can write the value C into D. So here in place of Q square, we put the value C square V square, and 2A epsilon naught remains as it is. Here in place of epsilon naught A, we can write C into D, that capacitance into the distance or distance of separation or the separation between the two plates. So F is equal to C square V square in numerator divided by, in place of A epsilon naught, we can write the value 2 times C into D. So F is equal to CV square times 2D, CV square by 2D, that is the force of attraction between the two parallel plate air capacitor. Option number C is correct. Question number 4 that was asked in AIPMT 2011. A parallel plate condenser has a uniform electric field, that is E in volt per meter in the space between the plate. If the distance between the plate is d meter and area of each plate is A in meter square, then energy required in joule, that is the stored in condenser, is the energy stored in condenser we have to find out. So first of all, that capacitance of the parallel plate condenser is C is equal to epsilon naught A by D, that is the capacitance of parallel plate capacitor or condenser, that is given by the formula of C is equal to epsilon naught A by D, and potential difference between the plate is V is equal to ED. According to the formula of electric field is equal to minus dV by dl, that is your potential gradient. So V is equal to E into D, electric field into distance between the two plates. So energy stored is equal to U is equal to 1/2 CV square. So U is equal to 1/2. In place of C, we can put the value of epsilon naught A by D, that is the parallel plate capacitance, and V is nothing but ED. So V square is equal to E square into D square. So after simplify this equation, the energy stored in the capacitor U is equal to 1/2 epsilon naught E square A into D. Option C is correct. Question number 5 that was asked in AIPMT 2015. A parallel plate air capacitor of capacitance C is connected to a cell of EMF V volt, and then disconnected from it a dielectric slab of dielectric constant K, which can just fill the air gap of capacitor, is now inserted in it. Which of the following option is incorrect? First of all, in first case, there is a capacitor without dielectric. Now, in case 2, that dielectric constant having K, the dielectric slab of constant K is inserted between the two plate of capacitor. So the capacitance is increasing due to the dielectric insertion between the two plate. The new capacitance, the capacitance C dash is equal to K times C. Initial and final energy stored in capacitor is equal to UI is equal to the initial energy that is stored in capacitor. UI is equal to Q square upon 2C, and UF is the final energy stored in capacitor, that is Q square upon 2C dash. So in place of C dash we can write Kc. So Q square upon 2K times C, that is final energy stored in capacitor. UF is equal to Q square upon 2 times Kc. So delta U is the energy, the difference of energy stored in capacitor. Delta U is equal to UF final energy minus initial energy stored in capacitor, that is Q square upon 2 Kc minus Q square upon 2C. Taking Q square upon 2C common, in bracket the remaining term is 1 upon K minus 1. So in place of Q we can write the value of Q is equal to CV. So Q square, in place of Q square we can write here C square into V square upon 2C, in bracket 1 upon K minus 1. So delta U, that is a change in energy stored in capacitor. Delta U is equal to 1/2 CV square 1 upon K minus 1. That option is correct, that the change in energy stored in capacitor, the change in energy stored is 1/2 CV square in bracket 1 upon K minus 1. So this option is correct. We have to find out the incorrect option. Now V is equal to Q by C, that is without dielectric, the voltage or potential difference between the two plate of capacitor. V is equal to Q by C in case of without dielectric. There is no dielectric insertion between the two plate of capacitor. Now after inserting the dielectric having constant K, that new potential difference V dash becomes Q upon K times C. That means the voltage or electric potential decreased by 1 by K times to original one, that is V without dielectric is equal to Q by C. V dash is with dielectric, that becomes Q upon Kc. So V dash by V, it comes out to be Q by Kc, that is the ratio of these two equations. So V dash by V is equal to Q by Kc whole divided by Q by C. Q by C cut. So the remaining quantity on the RHS side, V dash upon V is equal to 1 by K. So V dash becomes V by K. So electric potential after inserting the dielectric, it is decreased by K times. So potential difference between a plate decreased by K times, that is also true. And energy stored in capacitor is also decreased by K times, that is U is equal to 1/2 CV square, that is without dielectric the energy stored in capacitor, that is U is equal to 1/2 CV square. Now with dielectric, the energy stored in capacitor U dash is equal to 1/2 C dash into V dash square. So U dash is equal to 1/2. In place of C dash we can write Kc, because the new capacitance after dielectric insertion, it increases by k times. So in place of C dash, we can write the value Kc and V dash square, that the potential is decreased by k times after inserting the dielectric having constant k. So V square by k square in place of V dash square. So after simplifying the U dash, that after insertion of dielectric between the two plate of capacitor, the new energy stored, that is U dash is equal to 1/2 CV square by k. So U dash is equal to, in place of 1/2 CV square, we can write U by k. So energy stored in capacitor is also decreases by k times. So A, C and D option are correct. The incorrect option is the charge on the capacitor is not conserved. It is always conserved. That the charge on capacitor is not conserved, that is incorrect statement. So in question number 5, option B is correct. Question number 6, a capacitor is charged by a battery, then the battery is removed and another identical uncharged capacitor is connected in parallel. First of all, a capacitor is charged by a battery, then battery is removed, then another identical capacitor, which is uncharged one, is connected in parallel with the charged one. Then the total electrostatic energy of resulting system is, it is decreased by factor of 2, remains same, increased by factor of 2 or increased by factor of 4. So first of all, this is the required diagram, that the C1 is the charged capacitor having the charge Q on it, which is connected to battery, then the battery is removed. Then C2, which is the uncharged capacitor, that is connected in parallel with C1. So C1 is the charged capacitor and C2 is the uncharged capacitor. The charge on uncharged capacitor is Q equal to 0 and the charge on capacitor C1 is equal to Q. So what is the equivalent capacitance in case of parallel combination? C equivalent is equal to C1 plus C2. These both are identical capacitance. So C plus C, it becomes 2C. That the equivalent capacitance is, in case of parallel combination, C equivalent is equal to 2C. Then total charge Q net is equal to Q plus 0. That the total charge on this combination is Q net is equal to Q plus 0, because on C1 capacitance it is Q and on C2 capacitor the charge is 0. So total charge is Q net is equal to Q. Now uncharged capacitor is connected in parallel, then Vc is equal to Q net by C equivalent. That the voltage, required voltage Vc is equal to Q net by C equivalent. Q net is equal to Q after connecting uncharged capacitor in parallel with a charged capacitor. So Vc is equal to Q net by C equivalent. So it becomes Q by 2C, and in place of Q by C we can write V. So it is equal to, Vc is equal to V by 2. So what is the initial energy stored in capacitor? Ui is equal to 1/2 CV square, and final energy stored in capacitor is equal to 1/2. The C becomes 2C and V becomes half. That is, in place of Vc we can write V by 2 after connecting uncharged capacitor in parallel to that of charged capacitor C1. So the final energy stored in capacitor 1/2. The C equivalent becomes 2C and V becomes V by 2 whole square. So after simplifying, the final energy stored in capacitor 1/2 is equal to 2C times V square by 4. So it is equal to 1/2 CV square by 2. So in place of CV square by 2 we can write Ui. So final energy stored in capacitor, it decreased by factor of 2. So total electrostatic energy of resulting system decreased by factor of 2. So option A is correct, that the final energy or total electrostatic energy of resulting system is decreased by a factor of 2. Question number 7. Two thin dielectric slab of dielectric constant K1 and K2. The dielectric constant K1 is less than K2. That means here K2 is greater than K1. Are inserted between a plate of parallel plate capacitor as shown in figure. The variation of electric field between the plate with distance d as measured from the plate is correctly shown by. That is, we have to find out the correct graph between electric field and distance of separation, or the distance between the two plate of capacitor. So first of all, the electric field in the presence of dielectric, it is decreased by a factor K. So E becomes E naught by K, where E naught is nothing but external electric field in the absence of dielectric. So E naught is the external electric field and K is the dielectric constant. So electric field in the presence of dielectric, it is decreased by a factor K. So E is equal to E naught by K. Here the dielectric constant K1 is less than K2. That means the E1 is greater than E2, because in the region of K1, that E1 is strong as compared to E2, because the dielectric constant of K2 is more than that of K1. So E2 is less than E1, or you can say E1 is greater than E2, because K1 is less than K2, that's why E1 is greater than E2. So the electric field in the dielectric having K1 region is more than that of the electric field in the K2 region. So electric field in the region of K2, that is E2, that will be much lower than electric field E1 in the region of dielectric K1. So the answer is C, because here E1 is more than that of E2 due to K2 is greater than K1, that's why E1 is greater than E2. So the electric field in this region is more or higher as compared to this region, that's why option C is correct. Question number 8. A capacitor of 2 microfarad is charged as shown in diagram. When the switch S is turned to position 2, the percentage of its stored energy dissipated as. That was asking NEET 2016. We have to find out the percentage of energy dissipation. When the switch is at position number 1, Ui is equal to initial energy stored is equal to 1/2 CV square, and C is given as 2 microfarad, because when the switch is in position 1, the equivalent capacitance is equal to 2 microfarad and the potential difference is V. So Ui is equal to 1/2, in place of C we can write 2 microfarad, and here is V square. So the initial energy stored in capacitor Ui is equal to V square microjoule. When the switch as is moved at position number 2 or at point 2, delta U, the change in stored energy, delta U is equal to UF minus Ui, that is final energy stored minus initial energy stored. So it becomes that 1/2 C1 into C2, that is your C equivalent, because these two are in parallel, these two are in series, because at position, when the switch is moved at position number 2, these two are in series. So in case of series combination, C equivalent is equal to C1 C2 divided by C1 plus C2. So based on this formula, we can write the change in stored energy, delta is equal to UF minus Ui, and that is your equivalent capacitance. So 1/2 equivalent capacitance C1 C2 by C1 into C2, and that is your delta V, that is V minus 0 whole square. Because in first case the potential across this combination is V, but in second case when the switch is moved at position number 2, that is potential is 0, that's why the potential difference V minus 0 whole square. So 1/2 in place of C1, that is 2 microfarad, in place of C2, that is 8 microfarad divided by C1 plus C2 here, that is C1 plus C2. So 2 plus 8, it becomes 10 in denominator into V square. So it comes out to be 4 by 5 V square microjoule. That is your energy stored in change in energy or energy stored in capacitor, that is delta U is equal to 4 by 5 V square microjoule. Now percentage dissipated energy, we have to find out the percentage dissipated energy, that is delta U, that is UF minus Ui in numerator divided by Ui, that is your initial energy stored in capacitor, into 100, that is delta U is equal to 4 by 5 V square. In place of Ui we write here V square. So after simplify this, 4 by 5 multiplied by 100, it comes out to be 80%, that the energy dissipation in case of percentage stored energy dissipated in percentage, it is 80% from this formula, that is delta U, that is change in energy stored, delta UF minus Ui upon Ui into 100. So it comes out to be 80%. So option number A is correct for question number 8. Question number 9. An isolated charge plate capacitor is having charge Q. A is the area of plate, D is the separation between the two plates, match the column A and B. The electric field between the plate, that force between the plate, energy density between the plate, and potential difference between the plate. So first of all, the electric field between the plate is given by the formula E is equal to sigma upon epsilon naught. So that is the net electric field between the two parallel plate of capacitor, that is E is equal to sigma by epsilon naught, and sigma is nothing but surface charge density Q by A in coulomb per meter square. So E is equal to Q by A epsilon naught. So for E, that is the electric field between the plate, it is equal to Q upon A epsilon naught. For energy density, that is rho E, that is equal to 1/2 epsilon naught E square. In place of E square we can write E is equal to sigma by epsilon naught, that is the net electric field between the capacitor parallel plate capacitance. So 1/2 epsilon naught, in place of E square we can write C square sigma square upon epsilon naught square. So in place of sigma again we can write Q by A, so sigma square is equal to Q square upon A square. So after simplifying the energy density rho E comes out to be Q square upon 2 epsilon naught A square. the force between the two plate F is equal to CV square by 2D. So put the value of C, that is C is equal to parallel plate capacitance is equal to epsilon naught A by D, and in place of V we can write E into D. So V square becomes E square into D square. In place of C we can write epsilon naught A by D. So it comes out to be sigma square A by 2 epsilon naught. In place of E we can write sigma upon epsilon naught, that is E square becomes sigma square upon epsilon naught square. So after simplify, the force between the two plate of capacitor comes out to be Q square upon A square into A by 2 epsilon naught. So F is equal to Q square upon 2A epsilon naught. That is the force between the two plate of capacitor. And potential difference V is equal to E into D between the two plate is given as E is equal to, from this equation, E is equal to Q upon A epsilon naught. So write the value of E is equal to Q upon A epsilon naught into D. So V is equal to QD upon A epsilon naught. So the required answer is second. In question number 9, option B is correct. Question number 10, the electrostatic force between a metal plate of isolated parallel plate capacitor C having charge Q and area A is, that was asked in NEET 2018. That electric field due to one of the plate of capacitor E is equal to sigma upon 2 epsilon naught. That electric field due to one of the plate of capacitor, that electric field E is equal to sigma upon 2 epsilon naught. The force on one plate due to second one, that the force exerted by one of the plate on other one is F is equal to QE. So in place of E, put the value sigma upon 2 epsilon naught. So the force on one plate due to another plate F is equal to sigma Q upon 2 epsilon naught. So it is independent of distance between the plate. So option number B is correct, that the force between the plate of isolated capacitor is independent of distance between the plate or separation between the plate. Option B is correct.